If you're a Web3 developer, you probably live and breathe Solidity. And look, it's a fantastic language. But if you really want to build those hyper-optimized, super secure, gas-efficient smart contracts, you've got to go deeper. So today, we're popping the hood and diving right into the Ethereum Virtual Machine itself.
And yeah, that's pretty much the theme for this whole explainer. To really level up your skills, to break through that ceiling, you have to understand the machine your code is actually running on. All right, let's get into it.
So why is this so important? Well, because the EVM is basically the global computer that's processing every single transaction and smart contract on Ethereum. Understanding how it works isn't just some academic exercise. It is the key to writing truly superior code.
You know that really elegant line of Solidity you just wrote? Well, the EVM has no idea what it is. It only understands one thing, bytecode. And that bytecode is just a long stream of really simple one-byte instructions we call opcodes. Think of it like translating a beautiful poem into the raw ones and zeros a computer can actually process.
Now, to execute all these opcodes, the EVM has to juggle data between three very different locations. And let me tell you, knowing the difference between these is absolutely fundamental if you want to understand gas costs and optimization. So let's break them down.
First up, we've got storage. The best way to think about this is as your contract's permanent hard drive. Any of your state variables, like, say, a user's token balance, they live here forever. But because you're permanently writing to the global state of the entire blockchain, using storage is incredibly expensive.
Next up is memory. Now this is like your computer's RAM. It's temporary. It gets completely wiped clean after your function is done executing. It's the perfect place to hold data for complex calculations during a single transaction. And the best part? It's much cheaper than storage.
And finally, we get to the star of the show for our purposes today, the stack. This is the EVM's calculator, its main workspace. All the opcodes, they grab their inputs from the top of the stack, do their thing, and then put the results right back on top. It's the beating heart of the EVM, and you're going to love this. It is dirt cheap to use.
So the one rule you have to know about the stack is last in, first out, or LIFO. The best analogy is this stack of plates right here. You can only push a new plate onto the top, and you can only pop a plate off from the top. You can't just reach into the middle and grab one. That strict order is everything. It's also good to know that every single plate is a 32-byte word, and the stack can only go 1,024 items deep.
Okay, so that's the theory. We've talked about this LIFO plate tower. Now let's see how it actually works when the EVM executes a super simple line of code. We're going to trace an addition operation step by step.
All right, before we start the trace, here are the four main tools the EVM uses to mess with the stack. You've got push to put things on, pop to take them off, dupe to duplicate an item, and swap. Well, you can guess what that does. These are the basic building blocks for everything that's about to happen.
Okay, let's trace this one line of Solidity. C equals A plus B. First, we push the storage location of A onto the stack. Then, we use sload to replace that address with its actual value. We do the exact same thing for B. Push its address, then sload its value. Now, the stack has the values of B and A. The add opcode comes in, pops them both off, adds them together, and pushes the result back on. Finally, we push the storage spot for C, swap the items to get them in the right order, and then bam, stores saves the result permanently. Isn't that wild? A whole meticulous dance of data for just one simple addition.
Now, that was a pretty cool technical exercise, but you might be wondering, why does this matter? And the answer, my friends, is one word: gas. Every single one of those little opcodes costs gas. And as you're about to see, not all opcodes are created equal. Not by a long shot. And this chart, wow, this says it all. A simple add operation on the stack costs a measly 3 gas. You can barely even see it on the chart. But reading from storage with sload, that bar shoots up to 2100 gas. And then, writing to storage with ssstore, a mind-boggling 20,000 gas. The difference in cost isn't just big, it is absolutely enormous.
So here it is, the golden rule of thumb. Operations happening on the stack or in memory, super cheap. Operations that have to go and touch that permanent storage, brutally expensive. This is probably the single most important rule you need to know for gas optimization.
And that's really the big takeaway here. If you want to write truly efficient code, your goal should be to live on the stack and in memory as much as humanly possible. You want to minimize every single time you have to touch that expensive hard drive, the contract storage.
Do all your heavy lifting with cheap operations first, then do one final expensive save at the very end.
You know, when you really internalize these concepts, you're not just writing Solidity anymore. You're basically architecting how the EVM itself is going to execute your logic. And that knowledge, that becomes your developer superpower.
Think about it. Instead of just guessing why a transaction ran out of gas, you can literally visualize the stack as the code runs. You can see exactly where the inefficient operations are happening. Debugging becomes this precise science instead of a frustrating guessing game. You'll build better, faster, and cheaper contracts, all because you truly understand the machine. And that pretty much brings us to the end. You now have the foundational knowledge to really start mastering the EVM. I know it's a deep topic, but trust me, it pays off in huge ways. So, for all the developers watching, I'll leave you with a question to chew on. What's your favorite, or maybe your most hated, opcode to work with, and why?